Okay, everybody, let's get started for today's class. So before we do that, homeworks, and everybody can hand in here if you haven't put it here, please.
I emailed mine to you, is that alright?
That's also fine. I saw your email.
Okay.
Did you scan your handwriting? I haven't opened
I just did it all.
Okay, good, good. Modern way, 21st century, electronic. Let's get started for today's class. So, first, congratulations, everyone. This is the last chapter. Okay, you guys, I would call it 70% over the courses. In the last two major chapters, we did a lot of polymer physics calculation in a single chain, then solvent. So what is left?
Chapter 10, polymer.
What, chapter 10?
Rubber elasticity.
Rubber elasticity. Your favorite? Oh, good, good. So today's lecture is talk about solid state of polymers. So we moved from ideal chain, where we talk about Gaussian chain, etc. We then talk about solution phase diagram. So you can think about it as dissolving the material in the solvent. So starting chapter 10, we're going to cover several important aspects of that. If you guys had a chance to look at the book, it will talk about two important things. First is polymer gel, where we're going to talk about, it's actually fairly straightforward. We're going to spend today's lecture to chat a little bit about what is gel and what is gelation point and how do you quantify that. So after we talked about the gel part, next step we'll start to talk about solid states of polymer chain. For me, that's most important thing in terms of solid state, because in the end, every polymer you hold more or less is a solid state property of it. You know, either be I like to use Nathaniel's cup as an example. The top of lid, it's the solid condensed phase of your material. Your phone cover is also a solid condensed state of your material. So broadly speaking, there are two types of solid state of material. It can be either rubbery material or elastic thermoset material. Okay, and in the today's lecture, we actually will mostly focus on this chapter is on rubber elastic state of the material. So before we talk about that, one of the things we need to cover is another unique property of the polymer, that is viscoelastic versus so broadly speaking, we want first to clarify a few concepts. That's the first concept we need to talk about for condensed phase. So what's the definition between these two different property? At what circumstance you would call your material is in the viscoelastic phases, while the other one is in the glassy state? Do you know, Nathan?
I'm thinking of a spring and dashpot when you say viscoelastic.
That's a good model while people describing the viscoelastic property. That's a good call.
Are we talking
Chris?
about like a glassy thermoset, or glassies and amorphous, or I guess both?
Both, actually. So this at the beginning, we just gonna mention this because that's some of the unique property of your material. That is related to called a glassy transition temperature.
As in no rotation of polymer chains.
that's a very good do.
That'd be glassy.
Glassy, it's first let's talk about what this means. So if you look at a window, it's a glass, right? Glassy must be related or kind of close to glass. So what does that mean in this particular case? Glassy transition temperature is a description of a phenomena when your polymer or any material is being cooled. There is a deviation in its property. Okay, so if we do this, we think about this. I plot as temperature, and a very commonly measured technique is called a DSC. Okay, so you can measure heat capacity. Then if you look at heat capacity changes versus temperature, if you keep cooling, at some point it will deviate from its slope. And this is also reflected by, you can also plot volume expansion coefficient. So what does this plot is, similarly, you will have, say, one of your material. So this should be volume versus temperature. So this will be one slope. Okay. After that, it will be a different slope. So this tells you how much volume expansion is. So what does this tell you? Is in the glassy state, and this transition temperature, by the way, is just called the glassy transition temperature is called TG, or this temperature. Okay. And broadly speaking, this temperature basically tell you is your material is in the glassy state or not. On the other side of a glassy state, we actually call it the rubbery state, which will be tied into rubber elasticity. Okay. I'll give you a few examples of TG. So you can think about this is a temperature talks about your glassy state or non-glassy state. And glassy state, I mean, your material is in a relatively brittle state. Okay? Any question for this part? For example, we can think about polystyrene as everyday use. This material has roughly about 100 degrees Celsius TG. Okay, so this is very high, higher than room temperature, because we, as a human being, you want to put your scale bar close to the room temperature. That's where we are living or at or close to. So if that is much higher than room temperature, means at the room temperature, is your polymer in the glassy state or rubbery state? Glass. So it's a glassy state. So we can say at room temperature, polystyrene is glassy. What's a typical property of a glassy material? You think about glassy, brittle, rigid, hard. All these are kind of tied into a glassy property. Okay? We can now think about two different scenarios. Bless you. First is you have a material has a glassy transition temperature below room temperature. There exists as such a material. Can anyone name the example that a polymer has TG much lower than room temperature?
Polyethylene, polyacetylene.
That's all these are correct. Do you have one more to add on?
DNA and like
That I'm not sure. That I'm not 100% sure what the TG is. Some of the linear polyethylene is definitely will have TG lower than below room temperature, which means they are in roughly viscoelastic property. Or the other polymer is people know is polyisoprene. This is another low temperature, low TG material.
What about peak? Polyether?
That's very high. That's usually about 250-ish range. Okay, but the other, for example, linear PDMS. There is a very famous polymer made by Dow Corning called Silgar. It's their commercial name, 184. I need to put an R here because they're branded material. So this called Silgar 184 is one of the most commonly used soft rubbery elastic material. So what they sell you, I wish I bring a copy of that. What they sell you is a box where you open up, you got a large bottle of PDMS. Those are linear PDMS. And everybody knows the structure for the PDMS? Everybody? I think that's correct. So for this long linear chain, it will have very much low TG. What do you get? Open the box. It's like viscous honey. So you can think about that's a typical property for low temperature, low TG material. Okay? This would explain why this is not rigid or look like a glassy, it can flow. So coming back to this one, let's say polystyrene has a TG about 100 degrees C, right? So polystyrene, we know at the room temperature it's in the glassy state. How about heat the polystyrene up to 200 degrees Celsius? It will get into melt, or first to go into the viscous flow state, then go to the melt, right? Because that's dependent on how high you had the material above its TG. And TG should not be confused with melting point, Tn, okay? Tn is melt temperature. Where things getting melt and became liquid-like. So if you have a polymer sits between Tg and Tn, this is a very special state. And this is soft enough for you to bend it, twist it, getting a state called rubbery-like, okay? That's where a very unique property of a polymeric material where you don't have in any other system. Especially in metal, they don't have this intermediate state. There's another name called this rubbery state. They actually call it, like this bag, they call it leathery state. Like leather-like, because it's a little bit soft and stretchy at the temperature right below that. I want to plot another plot. I want to give the polystyrene as another example. So what we plot is elastic modulus of polystyrene versus temperature. Okay? Usually, this is about 4 gigapascal for polystyrene in the glassy state. So you can think about this this scale is very low temperature, much lower than room temperature. If you heat the material up, you will likely to get a slightly drop. Something looks like this. Then at about Tg, you will have a much bigger drop in terms of elastic modulus. And you will have a little bit plateau and a second major drop at the melting point. Okay? Is it clear?
Sorry, what is that? I didn't catch that part right there. What, right next to this one?
4 gigapascal.
4 gigapascal.
Oh, okay.
And this is typical on a megapascal level. You're talking about a factor tens of megapascal level. So the material just softened by a factor of 100. So how does this ties into what we're going to talk about rubber material? What would you guess? Will the rubber in the glassy state or in the viscoelastic state or some unique state that we haven't talked about?
Rubber?
Yeah.
I would say viscoelastic. This is the state that it's typically in.
Right. And we just talked about, that's correct. We just talked about for PDMS, if we talk about the seal guard while you open the bottle, it's liquid-like. That's typical state, right? Is there any magic we need to do to make the viscoelastic? Because I don't see the PDMS. Right at the bottle, it can be stretched and elastically returned to original state.
Oh, it's like it's PDMS is like liquid when you open it? Oh.
Yeah.
Okay, so you're gonna have to
A cross-linker.
or I mean, it might already be in there. It might need to be exposed to oxygen or something.
They depend on different ways you cross-link, right?
Plastic and stuff.
So, right.
Yeah.
So for the PDMS, it needs to be cross-linked. So what you get is a liquid-like material. I wish I can show you. So you get, if you pour a honey into a beaker, that's typically what is high molecular weight PDMS is. And you need to add a little bit of catalyst, which is cross-linking catalyst. You stir them, leave it at room temperature for about overnight or put in an oven for about 2-3 hours. Then you got a transparent disc, okay? And this is very stretchy and elastic. It is what is elastomer, and what we come into the conclusion what needed for elastomer, okay? Where elastomer is typically at viscoelastic state, and you can also say the Tg will be much lower than room temperature. That's requirement 1. Requirement 2 is typically need to be cross-linked. I can give you another example where you think about the natural rubber. It's one of the most item or substance used in the Second World War. Is how can you harvest rubber to make a tire? Anyone has any interest to understand?
Harvest the tree sap from a rubber tree. And
Yeah, harvest from.
kind of weird process. I don't know.
Got the first part right.
We had to start making it ourselves because it was tough to get it because it was in the South Pacific.
Yeah,
Usually where it was.
yeah. So that's how people harvested. First discover for the rubber is they cut a tree. They can actually something like maple syrup will be coming out. These are the monomers for the rubber, for the natural rubber. Okay, those is typically a linear diene structure that has Tg much lower than room temperature, and they need to cross-link. And typical cross-link is called volcanization. They add in sulfur, then they heat it up, then you have cross-link different parts. Okay. That's how you get a rubber. Is you need the first is individual linear chain. Look like this. I'll draw a few random chain, and need to be cross-linked by different locations. Okay. For example, we can also have cross-linker here. Why we need a cross-link then? Anyone can have advices while we pull the material. You think what's happening at molecular scale?
Break the disulfide bonds.
Then you wouldn't have it go back, right?
You get this like more solid-like behavior instead of the liquid-like.
They expand and stretch, but they don't break.
Right. Molly, good call. So that's what happens here. Is this is a too simplistic picture, but in more realistic case where there's still some chain, bending around, then there's one point. So where you stretch it at a very atomic scale, you extend this part. I mean, you overstretch it. Of course, you can break this. But let me give you a picture for one junction point between here and here. So think about this is one case between crosslink point. Between crosslink point. Okay, so this is a before stretch. So what after you stretch the rubber at the macroscopically, you're basically going to deform. At the atomic scale, it will deform the same as macroscopically. So what do you have? I'm going to draw it here. And something looks like this, right? So this point is being deformed by a new L prime. This is L0. Okay, so you can deform it this way. If you don't have this crosslink, what's going to happen is we talk about your material is in the viscoelastic state. It's just going to flow if you don't crosslink them. Then it's a phenomena also observed as in the viscoelastic material is stress relaxation. Think about you have a chewing gum. That's more like appropriate cases where we talk about here. If you have a bubble gum or chewing gum, or you pull it, you let it go, it didn't come back. It just stays as its shape, right? Well, for the rubbery material, if you have a rubber band, you pull it, you let it go, it come back. Or if you pull it, you leave it in an hour, you can still retract back, right? So you have to have the crosslink point to make this happen. And you have to have the secondary requirement is your individual chain must be mobile enough to slide it around or go back and forth. What about we have a material is in a glassy state if we stretch it? It's just going to break, right? If you pull a polystyrene straw or polystyrene fork or PLA, it's just going to break. The reason is your material don't have way to deform in low temperature. Okay, to summarize, you need these two to make an elastomer. Low TG, much lower than room temperature, and cross-linked point. Okay? Got it? And let's chat a little bit about this glassy phenomenon actually is a universal. Everything has a glassy temperature, glass point temperature. Another very commonly used or technique is glass blowing or glass art. So glass is amorphous material. So if you look at the window, its amorphous material has a glass transition temperature much, much higher than room temperature. Okay? So at room temperature, it is in glassy state. It will not move or do anything. and it's brittle. But once you heat it up, if you see any glass blower, what they do is they actually make it's above the melting a glassy point. You can actually start to stretch and deform and even blow, which makes them a circular shape. We don't have a glass shop here, right? We cannot do the glass art, but some of the chemistry department, they can do glass blowing or make their own glassware. Let's say you want to join two of the round-bottom flux. You can just put a linear glass tube and blow them and join them together. So you create a new glassware. Or even you go to art store or art shop, they can do all kind of glass art for you, right? So that's also glass transition phenomenon. So now we understand what happens at the molecular scale. So understanding this chapter is we need to understand what happens, what is forces need to deform it at the molecular level. So for the next field class, what we're going to do is to first understand how much forces need to deform a Gaussian coil. Again, a very simple model. If you think about a polymer chain, if you pull one end and pull the other end, if you start to stretching, how much forces that happen to your chain can be calculated. You can think about it's a hook spring, or any spring you buy, go to the store, you buy, or weight material, you actually get that, right? So that's something we will also talk about, is what the forces going to happen in that scale. Before we go into that far, next step is we're going to introduce some of the basic concepts in the mechanics of your material. So let's go from here. So we're going to introduce what is the stress and the strain and what is Poisson ratio, all these fundamentals into the mechanics of the polymeric material. Is there another class actually overlaps with this topic?
Continuum mechanics.
Okay, that's good. So you guys already know.
Yeah.
So someone can help me. What is, if we have a polymer rod, like rectangular shape, this is the surface area of A, this is the length of L. If I apply a force of F, how big is the strain? Stress on your rectangular polymer bar. So you have stress is equal to F divided by A. Wonderful. I don't think I need the second half of the class. Good. So now, if we have original L, now we have deformation of delta L, strain.
Delta L over L naught.
Times the modulus.
Nope.
That's a strain, right?
Place its stress. Oh, we already have that.
How about Joule ratio? Joule ratio. Let's make my life much easier with the other class. Joule ratio.
That one's new. Yeah, that's a new one.
That's a new one? Oh, good. I found the meaning of my lecture now.
Is it similar to Poisson ratio?
No. So it's actually fairly easy. So it's 1 plus strain multiplied by L. Oh, just 1 plus strain. There's no L. 1 plus the strain. Or this is basically L plus delta L divided by L. So it's a final length divided by original length. Right, Chris?
That's right.
Yeah. Good. So I feel I don't need to go through too much in this class. 3 parameters. And what we also need to talk about is Poisson ratio. This is a little bit idealistic. Let's call this as a height h. This is h. This is h prime. So after you draw it, there's a little bit of shrinkage in the perpendicular direction. So what would be the Poisson ratio?
Negative axial strain over horizontal strain.
And in this scenario, that would be it's typically written as this. We should have a delta H here in this direction. That is delta so the deformation in along the axis versus deformation perpendicular to that. So the typical Poisson ratio, no, it's the other way around. Delta H divided by delta L. So Poisson ratio for elastomer will be equal to 0.5 if it's perfect elastomer. So, okay. So elastomer means what we're going to talk about, rubber band, etc. So if you pull it, it's going to contract in the perpendicular pulling direction, and the contraction is half of what your elongation direction. Okay? And have in the other class, in the mechanics class, have you guys covered the concept of Young's modulus?
Yeah.
What is it? I think I'm doing a test for the class instead of teaching a new lecture, huh? What is what's E or Young's modulus? Easier. How about shear modulus? That's a good one. So we don't measure it, but how do you link the G versus the E?
E over 2, 1 plus B.
G equals to what?
E over 2. Over 2 times
E
1
over
plus
3.
Poisson's. Yeah.
I like the way he
Shear modulus is typically 1/3 of Young's modulus.
G will be equals to multiply.
Inverse though, right? Isn't that to the inverse?
It's dependent on which part you put on. So E elastic modulus will be 3 times. That should be in the, if you write E equals to G, that's the right way, yeah? Or the other way, it's going to be in the bottom. So for elastomer, if you put the Poisson ratio is 0.5, you typically will see this outcomes. Elastic modulus will be 3 times of shear modulus, okay? And that's a general relationship between E and G. Fundamental mechanics, wonderful. I think everybody got, it saved me half of the class to go through these. Perfect. I think we can already take a break, and while we come back, I can already move on to the next mini topics, okay? Fundamental mechanics, everybody already got it. Save me a lot of time. So 5 minutes break. While we come back, we can continue to talk about the gelation. That's a slightly different point, but we can use 30 minutes to cover that. It seems quite some overlap, huh?
Yeah.
For this part, what I'm teaching versus continuum mechanics.
Oh, I thought that was Michael's
The
hair.
Christmas baby sitting next to
Your
you.
hair smells so Christmassy.
Good.
We have a McCormick exam right after. It's
After this class,
Yeah.
when is that?
At 4:30.
Me too. I think it might be allergic.
Well, up
My
for the
tongue
good.
is itchy.
They used what they made last week.
You like this
and they
class
just-
better?
Yeah.
Huh?
You like this class better?
Which one? This one?
Bunch of bigger
I
X.
think that's it's a pretty straightforward class.
I reached out to you in 3 weeks.
I know.
And you spat on me.
Hey,
Well,
nobody said I was good.
oh, there's pretzels and Rice Krispies.
I threw the pretzels
Oh,
in there.
nice.
I went down a weird YouTube rabbit hole yesterday while I was eating dinner.
Just like Hannah.
And I ended up on that video. I was like, there's no way that's fake. This is trolling. And it was serious.
It's so real.
And I was like, wow.
British people, man.
1 in 30 men do steroids in the UK. That's the estimated number.
That's crazy.
Yeah, like straight up anabolic artificial
Prednisone.
testosterone. No,
Steroids.
No, like roids.
artificial T. Like you are putting in.
Who does that?
There's a steroid epidemic in the United Kingdom. It's like 1 in 30 men are on roids. It's
Jeez.
ridiculous. I wouldn't please
For sure.
Oh, it's you. Then.
Anyone want to go anywhere this weekend? I've got two $100 Southwest vouchers.
Yes.
I have to be used by this weekend.
By this weekend.
Yep.
Let's go to Vegas.
Let's go to Copenhagen.
Only one person can
Go.
go, so let's not get too ahead of ourselves.
Introduce some hiking.
Purchase it right now.
Have you been to Copenhagen?
Where should we
Dr.
go?
Boo?
No, where do you want to go?
Mhm.
Go to Nash?
No.
I heard good words about that. Could
Yeah.
be a fun
Have you ever
city.
been to Nashville?
No, Copenhagen.
Oh, Copenhagen.
Copenhagen.
Nashville, unfortunately neither, but I want to go.
To Nashville or Copenhagen? I'd rather go to Copenhagen than
Both.
Nashville.
Nashville, maybe a little bit of country music
Do you
there.
like country music?
Not too much, but no, I wouldn't oppose to.
You can learn how to line dance. Do you like Bloody Marys?
That's pretty good.
Do you like Bloody Marys?
Yeah, that's
They
pretty
have
good.
really good ones in Nashville. So that's a reason to go alone.
Uh huh.
Ones in Wisconsin. Like cheeseburgers on the top.
I want to go to Wisconsin.
My grandpa was like, "Do you understand alcohol drinks, don't you? What's a drink that would have green beans and bacon sticking out of it?" I was like, "Bloody Marys."
Bloody Marys.
He was like amazed. that there was- He's like, "There was bacon." Right. Bacon for my green beans. Did you guys see that wife swapped episode where the little boy goes, "Bacon's good for me"? No. Oh no! Yes, yes. I see the little
It's
chubby
like-
boy starts crying because
Yeah.
the healthy mom started taking away his bacon. Yeah.
Exactly. Is anyone else's brain just like as fried as mine is?
Yep. Stunning for a
Yep.
few minutes and take a break. Or you're gonna be fried from the test. Recent development or just current state in general?
Current state.
Okay.
Recent development.
Okay, no, because I've always been fried. This is not a new state of mind for me.
All over.
That's right.
That's really depressing. But
Big's job gave him a new cool jacket today with his name on it.
they just need to
Anybody
stop
wanna see
sending
it?
those graduation is approaching emails because I'm
Do I
just
need
like,
to?
no, it's
It
not.
Isn't that cool?
That's kind of cool.
Not even close.
Yeah, I would jacket like that. I'll probably
You
take this
you
one.
probably will get a master's degree as an interim one.
Yeah, maybe.
I heard they are trying to change the policy. They used to be you would get a master's degree only if you failed in a PhD, right?
Uh-huh.
Now I think there's some word talking about that. There might be some changes happening once you've passed your qualification exam and prospectus. You will give you a master's degree.
Oh, really?
No, we get that.
What?
Yeah,
We get our masters.
Yeah.
We get our masters.
Yeah.
That's cool.
Really?
The only reason is the state of Mississippi, they found we don't graduate very master's students.
So after the prospectus, so like that would be next spring,
Yeah,
right?
yeah,
Ish.
right.
So,
Okay,
that's how I'm feeling.
yeah. So graduation is close. So let's collect our mind back to the polymer physics. So in the book there was an interesting part where they combined the gels into rubber elasticity, I always found it's hard to teach them together. So I usually go through about 20-30 minutes to cover this gelation part. But I didn't personally think it's fitting in the rubber elasticity, or what we're going to teach in more general in the rubbery material aspect. Because rubber elasticity, up to now, we talked about the force and stress strain. So next step, what we're going to teach next Tuesday is when you have a Gaussian coil, what we're going to teach is we're going to get back to the chapter 1. If we hold the polymer coil, think about you are the Ant-Man, or much smaller than the Ant-Man, you're on the atomic scale. If I'm pulling one side of the polymer chain, and let's say Michael is pulling the other one, how much force we would get while we're pulling one single polymer coil? Okay? We're going to figure that out, Michael, in the real world. Okay, we can pull a rod together and as well in the imaginary world. So, coming back to the gel, what we're going to talk about gel. Since it's in the textbook, so it's my responsibility to talk about it. So what gel is, think about in the real life, when would you imagine there's a gel and when do you use it?
Gel reactor.
It's in between,
Gel reactor.
in between a solid and a liquid. It's a cross-linked liquid.
Well, kind of. So there's some cross-link to happen and make it sort of liquid solid-like. A great example is hydrogel, where 90%, 99, 95% is water. There's a little bit gel into that. Actually, the other day when I walked out of my office, there was one kit for teachers to show elementary kids what is super absorption material is. Anyone knows what these materials are? These are basically super absorbent material. So if you use, huh? What is that?
There's like this famous commercial where this guy is trying to sell this thing called a ShamWow because it absorbs a ton of water.
I haven't watched that, so I cannot comment that. But it's what this material is. It's looked like a polymer. If you add into water, it will absorb that a lot. It sounds like what you're talking about.
It's like the little animals that grow in the water.
Yeah.
Looks like you guys have more experience than I do, huh? For this water.
Get them for your kids. They're fun.
Okay. But it's very much related to mostly in cosmetics product, where you typically, hair gel is mostly is hydrogel or other diapers, for example. So how about why we need to talk about this today is where we're going to talk about when do you have material come from a dissolved state to gel state. And Rebecca mentioned that gelation reaction, right? So that's something we want to talk about today, not like super absorbing stuff. So now I want to challenge you guys to think about if I have dissolved some of the cross-linkable material, where in the backbone it has dp of n. So you have something look like this. For each segment, there's a cross-linking point. You can cross-link it. If I throw my material inside here, when do I would create a network? It's probably not best. Let me make this better. When do I would create a pathway where the whole system is gel? Where if I start from here, I can find the cross-link point, then move along the whole system. That typically.
When your degree of polymization reaches infinity.
When your dp is reached to infinity, but since it's a random cross-link, so you really don't have a mark to get the degree of polymerization. In that case, we basically call when do you react, and at which point you reach its critical gel point. And that's a parameter that we can we can approach, right? Or at the point the system is everywhere is connected. So it's about connectivity inside a gel system. Now coming back to this case, what typically happens in gelation is people talk about degree of conversion. So for your polymerization happens, how many bonds has been converted into cross-link point, and at what conversion rate your material will start to gel. That's a big that's a very big engineering aspect of reactor, where you need to think about and control the gelation point below or above what you want to achieve. So how do we approach this problem and understand when does your material start to gel? Is coming back to connectivity issue. Connectivity in gel system. So this connectivity asks you to understand when does it possible from A point to B point in your system is this realized. And this is typically done by understand reaction conversion rate, which is, let me make sure the symbol is matches with book. So this symbol is look at, this is usually written as P, as this is a conversion. I think should be conversion rate. So that talks about how much double bond has been reacted in this case, or cross-link point. So P, if I can give you an example. So if we think about the P equals to 1%, which means 1% of the double bond, or let's call it generally non-saturated bond, is reacted. Okay? So if this equals 100, then you have a pretty much fully gel state, okay, or fully converted state. But in a lot of cases, your material gels already way ahead of that. I can give you an example. Now think this is a reactor. We put the 3 chains or 4 chains. If you want gel this system, you only need, if it's lucky enough, you only need to cross-link here and here to make everything connected, right? So now, it doesn't require this double bond to be converted, neither this unsaturated bond. It's only required these 2 tiny fraction of reaction to be reacted. So then it comes to a critical point. If you look at this bond, if we say P multiplied by N and multiplied by N times, there will be the extent of reaction. X is just a number, okay? X is how many times you would react inside of the polymer bond. P is the conversion rate. N is number, how long your chain is. So if you have P multiplied by N is larger than 1, that means your system, this will go into infinity, or the chances you find next, an unsaturated bond in the neighbor chain will be much bigger. Everybody following this? Looks like we need to explain it one more time.
Yeah.
Let's try the, does everyone get the point? When does the gyration happens if you have cross-link point around different samples?
So it's just when all the chains are connected.
Right. So I guess the good way to explain is at the conversion rate of P. P is just a conversion rate. How many chances among these conversion points would it be the one from the other chain?
Oh, so like if you have 10 sites on one chain and only one of them reacts,
right,
reacted, then your conversion rate would be like 0.1.
Yeah. No, it will be 10%, right?
10%. Okay.
But if you n, let's actually do an example. Let's do an example that's easy to understand. So let's try a real-world example first. So if we have polyisoprene, so this is polymer, right? We have a molecular weight about 150 K Dalton. That's a molecular weight. And this is cross-linked. This is cross-linked by sulfur for vocalization. Okay, so we will cross-link until and the question is the sample in cross-linked state?
So isn't that going to depend on what our x value is?
It will depend what the x value is.
Can it be less? What can your x value be less than 1? Or is it just like 1 to...
No, x value is, it's infinity. So let's use a more simple way. So if we have the system is fully cross-linked, which means when, think about you are now this bond. You are here. You know the conversion rate is n multiplied by p. That's how many bond is reacted, right? So if we come back to here, what is your degree of polymerization? N will equals to molecular weight divided by monomer molecular weight, right? Monomer molecular weight. So monomer is about 68. Polymer is this much. So this is about 2. Roughly about 2.2 or 2.1. Yeah, if you can help me with that, that would be great. So this will be,
It's 2205.
let's call it 2200. So that's the degree of polymerization. So they are along a single bond, along a single chain. If we pull one of these chain out, you got this number of unreacted. So if conversion rate is 0.3%, how many bond is reacted?
Or is it 0.03?
No, 0.0003, 0.3.
Oh, wait.
It's 0.3%, so 0.0.
It's 0.3%.
Yeah. So you got
6.6.
Really? No way.
0.00, yeah.
Oh, 6 point.
Yeah.
Stupid professor problem. you got 6 points is reacted, okay, along the chain. That means you will have 6 points connect to the other bond that has 6 points, right? There's going to be another chain coming here, then some point along the way. So you already formed a network. Do you see the explanation here?
So is that 6.6 cross-links per chain, or is that?
Yeah, that's 6.
Just or 6.6 kind of branches that could possibly cross-link.
Right. So it's 6.6 reaction happened to that bond, and whenever that happened a bond, it's basically a cross-link point.
For sure, it's going to cross-link.
Right.
6.6 crossing points.
Yeah.
Per
Average
chain?
per chain, right? Because that's we calculated. On average, this will be this much bond. So when does the system just have about the cross-link point? There will be one cross-link point along the chain, right?
So, okay, it's got to be 1.
Right. So that's when you only have one reaction along your bond. It needs to be relatively uniform distributed. So in other words, the critical cross-link point is defined by P multiplied by N will be equal to roughly 1. Because whenever it's larger than 1, it will be exponent of 1.1 many times will be infinity, right? If this is a small n, e.g., example, P multiplied by N larger than 1, that's called, this will go into infinity. Think about this is 2. 2 squared will be 4. 2 to the power of 3 will be 8. This will quickly roll into infinity. If this is smaller than 1, P n will close to 0. The chances of you finding a bond from the next bond will be 0, right? So this is a critical graduation point. Or P will be 1 divided by N. If we use that as example, we know the critical point will be 1 divided by this value, right? So one bond is being reacted in your material that's good enough to create a total network for your system, okay? So what does that mean is you only need one bond to react with another bond, then another bond will react with this one, then this propagates. That's a critical point. Your chances the system is already have one gel, okay? So that depends on dP. So if you have a polymer with very high molecular weight, dP of 10,000, it gels much early, right? If you n will be equals to, let's say, 100K, gelation point, this is very low, so P will be equals to 1 divided by N will be equals to almost have a little bit of reaction, your system is already gel, okay? And the rationale is you have a long chain now. You only need to connect this with another one, then it will form long distance gel. Or it can be any point along the backbone, right? As long as you have a reaction. For the shorter chain, If n equals to, let's say, 100, then you need a critical point is about 0.01. Or you need basically 1% of conversion rate. Okay, that's when your systems are fully gel and your propeller will not rotate and make it move. And you need to break it to take off your stir.
So how does this change if you're just like going from monomer to cross-link network if you don't start with a long chain?
So that is more like viscosity change. It does not necessarily to be a gel in this case. In this case, we particularly talks about you have already a polymer chain, but you want to cross-link it with a cross-linker. Any question for the gelation part? It's relatively simple, right? It's just a very straightforward cross-linking point we need to master in this case. When does your system start to gel and how does it work out? In reality, actually, the molecular weight will have a polydispersity come into it. You will never have a perfectly monodispersed material. So your molecular weight will have a polydispersity. In this case, N will have polydispersity. So what you would get is P will be equal to inverse number averaged molecular weight above 1. Okay?
The number average degree of polymerization?
Yeah. So that would be correspond to basically number average molecular weight.
Yeah.
Okay? So this basically summarizes the gel part, and in this case, we covered when does the systems to start to gel. And you can think about the, along one polymer chain, there's multiple reaction point reacted or cross-linking point that you can think about this a critical gel point. Think about this, if along the one chain there's 3 cross-link points, you are likely to form a very large network. If the chances along one bond you found a cross-link point less than 1, then you wouldn't have a fully gelled system. Okay? All right, with that, we finished the first very short class. Thanks to Gopinas on this part. I should buy him a coffee. We speed through all these definition and terms, okay? So for the next class, what we're going to talk about is I'm going to get a rod or a chain or how can I say, or a cable, so we can demonstrate in class how do we deform for a single chain.
We love a good demo.
Demo.
And the key thing is we need to understand where is this force is coming from and how we can link it together to the first chapter, chapter 6, chain conformation. Because in this case, chain conformation is making a difference. Okay? Okay, good. Good luck for your test this evening. Then.
USM now offers a master's in polymer engineering.
It's not a done deal. That's what I heard. The rumor is what they're trying to.
When are they planning on implementing that?
I do not know.
Because that would be pretty awesome to have that guarantee. If you don't make it to PhD, at least you get a master's.
Yeah. I agree. I think that's would be interesting to see.
So that my from here would match. There wouldn't be any clashes for my one day beautiful office. I bought the hard cover books for this so that I can start my research.
I want to walk when I get my master's.
Some people
So I can walk just like a million times.
Yeah,
My family told me I get one. Just have a million graduations.
I've never done it. Skip my high school, skip my undergrad. I will be skipping my PhD.
Why? You get the million. They're like, you
I
weren't
didn't
gonna walk.
walk.
So the deal was in high school that if I